All right. Hi, everyone. I guess we'll get started. So the last call for homework number 8, that's due tonight. Okay. So there are 9 also available online, but yeah, just finish 8 by tonight. Okay. You can work on 9 later. Okay. So um, in the past, I have guess one instant that people are working on the wrong homework assignment when they are both online, like this one and next one, current one and the next one are both online. Some people were confused, but yeah, work on homework 8 that is due tonight. Okay. Um, so let's get started with chapter 13. We took a look one section last time, but let's take a quick look what we learned last time. So we learned Faraday's laws, which basically if you have a magnet, you can move it approach coils, several coils, then you'll have induced current inside it or induced voltage inside it. Okay, so that's Faraday's law. Now, the result of induced current is because you have magnetic flux changing. So magnetic flux is defined similarly to electric flux, which is the integration of the B field dot the normal direction of the surface, and then you integrate through the whole surface. Okay. If the quantities are not changing, B and A are not changing, and then the angle is not changing, so then it's BA cosine theta. Okay, so the theta is the angle between the B field and the normal direction of the surface. All right, so in that case, you can see you can have either change in magnetic field, you can have change in the area, you can also have change the angle to have the change of magnetic flux. Okay. For a solenoid that has many turns of coils in it, so if you have n turns of coil, then the flux will be amplified by the n. Okay, so multiply n BA cosine theta. Okay, so where A is the area of a single loop or single coil. Faraday's law gives you if you write it out as a mathematical expression, then it's epsilon equal to minus d phi sub m. That stands for magnetic field over dt. So a magnetic flux. Epsilon is the induced potential inside the loop. Okay. All right. And then again, if you have n turns of coils stacking together, you multiply it by n. Okay. Today we'll be checking. Start with checking on Lenz's law. So Lenz's law actually it says an induced current always flows in a direction that opposes the change that caused it. Okay, so that is again the similar to Faraday's law when we took at when we had to look at the equation in the previous slide. There's a negative sign. Okay, so the negative sign basically says the induced either current or voltage opposes to the change that caused it. Okay. So for example, if you have bar magnet, you approach it through this coil, then because you are going towards it, so then the magnetic flux through this coil will be increasing, right? So the magnetic strength will be increasing. Now, then it will induce a current inside the coil here. Now the inside of the coil, because you have current inside the coil, so it will have an induced magnetic field due to the induced current. Okay, so the current induced magnetic field, if you look at the field here, because you are approaching it, so then the field it induced should be opposing to the change. So if you approach a bar magnetic close to the coil, the magnetic field is getting stronger when it comes to the coil. The coil will feel stronger and stronger field. Okay, so then the coil will have the induced magnetic field that is in the opposite direction of this bar magnetic. Okay, so then in this tiny shape of bar magnet, this is the effect of this induced current that is doing here. So it induces a magnetic field just similar like a bar magnet. So it will be in the opposite direction of this guy. Okay. Now, if you are going away, then the induced magnetic field due to the induced current over here should have the effect that opposes this bar magnet going away. causes the magnetic field to be getting weaker at the position of the coil. So then the coil, the induced magnetic field by the coil should have the same direction as this bar magnet because it now opposes to the decrease. So then it makes up portion of the amount being decreased. Okay. So that's how you can tell what will be the current direction in the coil, either in this case or in the case. Okay, if you are approaching, you should expect the magnetic field to be in the opposite direction of this guy. So then that means the current is going in that direction. Okay, so then the B field is in that direction. Okay. Or you can do it this way. You can put your forefinger in the direction of the magnetic field, so then the current is in that direction going inside. Okay, on this case, it has to have a magnetic field going in this direction as the magnetic field line indicates. So then the current is going out of the board, okay, or in this direction. All right, so that's Lenz's law basically. Now let's take a look if you have a changing in area. Okay, so in this case, you have two rails, the thinner wires here. The two rails over here, and then that is connected to the a light bulb. Now you have a relative larger conductor, metal conductor here that can slide without friction. Let's assume that's the case along these two wheels. Okay, so in that case, then you can see there's a loop completed by this bar, the two rails, and then the light bulb over here. So there's a complete circuit there. This is a loop. You can take a look at it. So if this bar is moving, this conductor bar is moving, then you can see the area of this circuit or the loop is changing. Okay, so if you have changing area, then even though the magnetic field is constant, the external magnetic field stays the same, then the flux should still be changing because B times A times cosine of theta, A is changing, then flux is changing. So then you will have induced current inside this coil or this circuit. So then you'll see the light bulb being lit, okay, in that case. All right, so you're changing the area, then you are changing the magnetic flux. You can do it the other way around. You can make this guy move. Well, actually, I think this is the same case here. So then the magnetic, because there's a current inside the circuit over here, so then there will be a magnetic force on the bar here because the bar is moving down. So the magnetic force, according to Lenz's law, should be opposed to that movement, that motion. That motion goes down, so then the force will be going up. Okay. And you can determine, so in the previous slides, let's go back just one slide over here. If the bar is going down, so then the B field is constant, area decreases, so your flux decreases, right? So then there will be a current induced in the circuit here. If you have currents in the circuit, then you'll have induced magnetic field, right? So magnetic field, that the induced magnetic field should be opposes to the original change of the magnetic flux. So magnetic flux actually decreases because area decreases, right? So to oppose that effect, your induced magnetic field should be in the same direction of the original magnetic field because that's the added magnetic field, right? So then that will slow down the decrease of magnetic flux because you add that induced magnetic field. Okay, so magnetic field should be still being pointing outward here. So you can see, according to your right-hand rule, if magnetic field comes out of the paper inside the loop here, then your induced current should be in that direction to the left. Okay, so that's the direction of the current to the left. And because this current carrying conductor is in the magnetic field, so you will experience this magnetic force. Okay. So you can determine what will be the direction of this F. So you put your four fingers along the direction of the current. Actually, you'll be doing this way. And then you curve your four fingers towards the magnetic field. So then outward. So then the force will be upward, okay, in that direction. And that exactly opposes the motion of the rod going downward, okay. You can also determine it that way too. All right. Let's take a look on this example here. It says, as shown in the figure, a circuit has an area of 0.060 meters square, contains a R equal to 1.0 ohms resistor and a C equal to 250 microfarad uncharged capacitor. Pointing into the plane of the circuit is a uniform magnetic field with magnitude of 0.25 Tesla. In 0.010 second, the magnetic field reverses direction at a constant rate to become 0.25 Tesla, pointing out of the plane. What's the maximum charge, sign, and magnitude accumulate on the upper plate of the capacitor in the diagram? So let's analyze and then see what's the scenario over here, okay? Let me draw the circuit on the paper here. So we got a capacitor, we got a resistor, all right? And then the B field is in that direction, pointing out of the paper, or pointing into the paper, sorry. It's, it's the cross going into the paper, so that's the B field. So then we can see there's this loop by this circuit. It's a loop over here, right? So if you have now your B field is changing, it reverses direction, okay? So it goes from 0.25, let's say that's positive, and then to negative 0.25, okay? To negative 0.25. Delta t is 0.01 second. That's the time it takes. All right, so the area of this loop would not change, right? And then your magnetic field is in the same direction as the normal direction. So the magnetic flux should be equal to B times A. The cosine theta, that will be 1 because theta will be 0, okay? If your B is changing, then your flux is changing. Then you will have induced EMF here. So you will have an induced EMF, which is derivative of magnetic flux over dt. That is equal to minus dB over dt times A, right? Because flux is equal to B times A is constant, then the change will be just the B field. All right. So you have induced electric potential there inside the circuit. Then the induced potential will be on the capacitor, right? So let's see. Initially, it goes into the paper. The B field goes into the paper. Now it's changing. So from say positive and then change to negative. Negative means for final B field, this is going to be pointing out of the paper. The B field final, the B field initial, B field final will be pointing out of the paper. Okay, B final. So let's put it that way. In this case, you can see, so to oppose that change of B field going from into the paper to out of the paper, right? Then your induced B field by this loop should be going into the paper, right? So this would be the B induced, okay? Due to the current in the circuit. All right, so then B field is going into the paper inside the circuit, okay? So we, for outside of the circuit, then it will be a different story because if you have your four B field coming into the paper in this case, then you put your 4 fingers into the paper inside the region of the circuit. So then the current is in that direction on this wire, okay? And then it will be in that direction on the top wire. So this would be your induced current direction, I induced, right? In the wire. So that means the current is going in the way. So then you will have positive charge on the upper plate. You have negative charge on the lower plate because of the currents moving. Okay. All right. So let's see. What are we looking for? It's asking what's the maximum charge Q, okay, on the upper plate. So I think we have determined that on the upper plate, you have positive Q, right? On the lower plate, you have negative Q because of the induced current is floating in that direction, okay? So now let's see. So in order to calculate what's the charge Q there, we need to know what's the the voltage, right? In this case, the voltage will be the induced voltage, okay? So we can calculate what's this, and then we can have our epsilon, okay? So epsilon is equal to minus dB over dt times A. So minus dB is changing with a constant rate, okay? Or it actually tell you so initial and final, and then the change in time t. So you can do delta B over delta t times A, which means final minus initial over there. Okay, so final, there's a negative here, 0.25 Tesla minus initial 0.25 Tesla. This is B final, this is B initial, divided by delta t of 0.01 second times the area. It tells us the area 0.060 meters square. Okay, so epsilon will be equal to when you plug in your numbers, it tells you 3.0 volts. Okay, for the induced EMF. Okay. Now, so that's the voltage induced in the circuit. Okay, so we can see how much charge would that be then. Q is equal to C times epsilon. So epsilon is kind of the power supply to this circuit, right? So C times epsilon. So C is given as 250 micro minus 6 farad times 3.0 volts. That gives you 0.75 times 10 to the minus 3 coulomb, okay? So that's how much, or we can say 0.75 millicoulomb, okay, of charge being will be on this top here, okay? Now, there's this question of, we actually have R here. What does that have to do with the problem here, okay? So let's take a look here, because this is then an RC circuit. Then what will be the time constant? The time constant then will be tau equals to R times C, right? That's equal to 1 ohms times 250 microfarad, okay, times 10 to the minus 6. So that gives you 250 microseconds, okay, or 0.25 times 10 to the negative 3 seconds. That's your time constant, all right? Now for the whole process of the magnetic field changing is 0.010 seconds. So that's, compare this guy to that guy, it's much less than, or much less, we should say, much less than 0.01 second, because this is a quarter of millisecond, right? 0.25, and then this is 10 milliseconds, okay? So this guy is 40 times of that, all right? And in that case, because you have induced current here, this is equivalent to an induced EMF, or you can imagine then there's a power supply over here to supply that, okay? So for the circuit, you can simulate it as a power supply, and then a resistor, and then a charge, the plate, the capacitor, 2 plates, okay? So this will be the induced EMF by changing of the magnetic field, okay? So in this case, this is an RC circuit, right? So if your T, the delta T it takes for this change is much greater than your tau, then this guy will be fully charged, okay? Now, the RC constant here tells you if this will be almost fully charged. So in this case, because it's 40 times of that, okay? So if your delta T in this case given is very close to this tau, so if it has the same order as of tau, then according to a RC circuit, then if this is just 1 times of tau, then it's actually not fully charging, right? So you cannot use this to calculate. It's still in the charging process, so you cannot use this to calculate the final charge, okay? You might just, you would have just less charge than in this case, because delta T in this case, 0.010 seconds is much greater than your time constant tau, okay? And then for this week's lab, we'll take a look on the charging process of RC circuit. So it takes about 4 times of the time constant to get more than 98% charged. Okay, so after the 4 or 5 time constant, then we can say approximately your capacitor is fully charged by that point. Okay. All right. Any questions you guys might have on this one before we move on? All right, if we are clear, then we can move on over here. So the next section here talks about motional EMF. So that's the potential induced due to the movement of a rod here. So this is again similar case here. You have a rod that is a conductor. You have 2 rails that is made of 2 wires and then connect to a light bulb over here, or it could be a resistor in this case. Now, if you can make the rod move in this direction, actually either direction, you can have induced EMF or induced current, in either induced voltage or induced current inside the rod here, okay? So that's called induced EMF or induced or motional EMF, all right? So if this is the external force that you used to pull this rod and make it move, then the magnetic force the rod experience due to the induced current inside it will be in the opposite direction, okay? Because according to Lenz's law, the induced current will oppose to the change that caused it, okay? So this is the external field is the cause of the motion, and then the induced current will oppose to that due by having this induced magnetic force, okay? All right, so let's take a look how much EMF is being induced in the case. So we'll start with the change in magnetic flux. So in this case, you can keep the B field, the external magnetic field constant because your rod is changing. So the area of your circuit is changing, or the area of the loop is changing, okay? And how much area changing delta A, we can go to the previous slides here. We can see after delta T time, then this is amount of the area changing by this rectangular, okay? So it will be equal to the length of the rod times the distance it travel, L or V times delta T. So L times V times delta T will be your delta A, okay? So VL delta T, that's your delta A. So for the induced EMF, if we just take a look on the magnitude, that means we are doing absolute value. So we can get rid of the negative sign, okay? That should be equal to the number of loops you have. In this case, you have only 1 single loop, okay? So N equal to 1, delta phi over delta T, okay? Delta phi is this guy over delta T. So you can see delta T and delta T would cancel. So your induced EMF would have a magnitude of B, the magnetic field, times the speed of the rod, and times the length of the rod. Okay, so BVL, that's the induced EMF. Now, because inside the rod you have induced EMF, you can imagine if you have potential difference across the two ends of the rod, then there will be electric field inside the rod, right? So the electric field will be equal to the potential divided by L. So all the length of the rod. So epsilon divided by L, which is BVL divided by L. So L will go away. So the electric field is equal to B times V, okay? Now we can take a look on what's the magnetic force that the rod experience. So the rod will experience the force equal to I, the induced current times L times B. I will be equal to the epsilon. So we in the previous slides we see this is epsilon, right? Induced potential divided by R times L times B. So then it becomes B squared times V L squared over R. Okay, so this is the magnetic force that the rod will experience. Now, if you would move the rod at constant speed, that means your external force should be equal to this magnetic force. Okay, so this will be the magnetic force as well as the external pulling force if your rod is moving at constant speed. All right. Now let's take a look what will be the mechanical energy on mechanical power that is required to pull the rod at a constant speed. So we know that force power is equal to the force times the speed, right? So the force is B squared V L squared over R from the previous slide times V. So that mechanical power needed to pull the rod to move at speed of V is equal to B squared V squared L squared over R, okay? Now, because you have induced current I in the loop, so then the light bulb will consume the power due to current going through it. And then that should be equal to I squared times R, if R is the resistance of the light bulb. So then I is equal to epsilon. Again, epsilon is equal to BVL, right? And then I is equal to epsilon divided by R. So then if you square it times R, you'll see that there's R squared in the denominator will cancel out R here with one R remaining. So then it's just R in the denominator, but on the numerator, you'll have B squared, V squared, L squared, okay? So compare this electrical power, the light bulb is consuming with the mechanical power that needed to pull the rod moving at constant speed V, you will figure out they are identically the same, okay? So that's because what your mechanical power does is what it is done to the mechanical power is it's being converted to the electrical power, okay? So this is the pretty much the principle of electric generator. So you are converting mechanical power into your electrical power, okay? In this case. Any questions you guys might have before I move on? All right, so if not, we'll take a look on this example here. It says the figure below shows a zero resistance rod sliding to the right onto zero resistance rails separated by the distance L equal to 0.5 meters. The rails are connected by a 10 ohms resistor, and the entire system is in a uniform magnetic field with a magnitude of 0.750 Tesla. Find the speed at which the bar must be moved to produce a current of 0.175 amps in the resistor. All right. I think you guys can give it a try on this one, and then we'll take a look on the solution together just in a couple of minutes, okay? All right. So let's see. We know that induced EMF is equal to BVL, right? And then it tells us the induced current, which is epsilon over R, right? That's equal to 0.175 amps. It's asking us to solve for the V that needed. So basically, we can replace the epsilon here with BVL. And then we can solve for the V because our other quantities are given. So BVL divided by R is equal to the I, the current. So then V will be equal to I times R over B times L, okay? 0.175 amps times the 10 ohms divided by the B field of 0.75 Tesla times the length of the rod, 0.5 meters, okay? So V then will be equal to 4.67 meters per second, okay? I think most of you guys submit your responses, got this one right. All right. Questions you guys might have on this one? All right. So if not, then let's move on to a second example here. So this one says a short rod of length moves with its velocity v parallel to an infinity wire carrying a current. If the rod is, if the end of the rod nears the, let's see. Yeah, if the end of the rod near the wire is a distance b from the wire, what's the EMF induced? Okay, so it's asking what's the EMF induced in this rod. Okay, now this is slightly different from what we've seen in the previous problem where basically you have a rod that is moving on this guy, right? Now in that case, you will have induced EMF here. So then this can be used as a power source to power the circuit. In this case, in the problem here, you have this rod that is moving in the magnetic field produced by this current carrying wire. But then you will only have induced EMF here for the rod, and it's not used to power any circuit. So you only have induced EMF, you will not have induced current. Okay, so this is what this will do, because you can imagine, so the rod is moving, that means the electrons inside the rods are moving, right? So then electrons are moving with the rod, then you will experience magnetic force due to the wire is carrying current, it will induce a field nearby here. So then the electrons will experience magnetic force, will be moved to one side of the rod. Then the other side of the rod will be positively charged. One side will be negative charge, the other side will be positive charge. So there will be magnetic field inside the rod and potential difference from the two ends of the rod. Okay, so that's basically what it's going to happen. But we can actually analyze the scenario here similar to the problem in the previous case. Okay, so in this case, you have a rod carrying current, a wire carrying current I. Okay, so then there will be magnetic field induced by this I. So you are going to point your finger, your thumb in the direction of current, your forefinger curls in the direction of the B field. So on this side of the paper, B field will be going into the paper. Okay, so that's the B field. On the other side of this will be coming out of the paper. Okay, because it goes in, comes out. Okay, on the other side. Now let's say if you have a rod here that has a length of A, and then this distance is B. Okay, you can assume that this rod, if it says it moves with velocity v parallelly over, so you can imagine after delta t of time, it will move by the amount of v times delta t. Okay. So then in that case, we can imagine if there would be like two rails as the case we saw earlier, then this would be the change in area, delta A, change in area, okay? Now, in this case, you don't have actually homogeneous B field over here, right? Because B field here induced is equal to the magnitude of the B field is equal to mu naught times I divided by 2 pi r, distance r. So if you are here, then your B field is mu naught I over 2 pi b. But so this is on this point. But if you are over here, your B field is actually mu naught I over 2 pi a time a plus b, right? It's different. Okay. So you cannot simply just say to calculate flux, you cannot simply do B times A in this case, right? Or change in flux would be, if we are looking for change in flux, then you should be doing change in B times A, right? Now, area is changing, also B field is changing, okay? So in that sense, you have to do, just pick a small slice of this area over here. And then we are going to say this is the distance R, okay? And then this is dr, the thickness of this guy is dr, okay? So then you'll have to do it that way, B field times that, okay? So for this small thickness, we can assume that B field to be constant, right? So B times the change of the area of A here. So for the flux over here, we will have to say this is D flux, small area. So it's the B field times the area, okay, of this line should be equal to its length times the thickness. So will be the V times delta T times dr, okay? V times delta T will be the amount of this length over here, and then times dr. So then for delta flux, magnetic flux should be integration of d flux, okay? Equals to integration of b v delta t and then dr. And then you should integrate from b here all the way to the other side of the rod. So from b to a plus b, okay? And your b field at distance r away, that is, so b a plus b mu naught times I over 2 pi r. That's your b times v times delta t dr, okay? All right, that will be equal to your change in magnetic flux. All right. You can put the constant terms in front of integration. So mu naught I 2 pi, and then v is not related to the r distance. Delta t is not related to that, but 1 over r dr from b to a plus b. Okay. So then this would be integration of 1 over r dr. That will give you ln of r, right? Natural logarithm of r b to a plus b. And then this is mu naught I 2 pi V times delta T equals to your delta phi over M. Okay. And then for the EMF, if you look at just the absolute value of it, that should be equal to delta change in flux over change in time t, right? So you kind of move this guy to the other side of the equation to become this. So then it'll be equal to mu naught I 2 pi times V times you put in the upper limits and then minus the lower limit. That will give you ln of A plus B minus ln of just B, right? So then your epsilon will be equal to mu naught I times V over 2 pi ln of, if you do ln A plus B over or minus that, will be giving you A plus B over B. Okay. So then that will be your final result for the induced EMF in terms of the given variables in the problem. Okay, so given variables are I, velocity V, and then A and B. Okay. Any questions you guys might have on this one? Okay. So if that's clear, we'll move on here. So because we have induced potential inside the rod, then you can expect there's an induced electric field. Okay, so in that case, so you can also calculate what's the induced potential if you know the induced field. So it'll be integration of E dot dl. So if this is a closed loop, then you are going to integrate through the whole loop. Okay. And induced EMF is also equal to minus d phi over dt. So change in flux over dt. So then you can have this equation. All right. Now this equation applies into two scenarios. So when you have induced EMF, then this is not equal to 0. Okay. If you don't have induced EMF, if this is just pure electrostatic, then actually if you integrate through the whole circle, it's going to be, if it's a closed path, it's going to be equal to 0. Okay. So this is what we see when we apply the loop rule for the Kirchhoff rule. So you are basically starting from one point and then going all the way through and then coming back to the original starting point. You will get 0 for the potential change. Okay, so basically this will give you potential change. Now, in the case of if you have induced EMF, then that's different. Okay, so if you are going from one point and then going through a whole loop, coming back to the initial point, then actually you will have potential difference there. Okay, that's not equal to 0. All right, so that's on that section. So next we'll be taking a look at eddy currents. So the eddy currents are loops of electrical current induced within the conductors by changing magnetic field in the conductor due to Faraday's law of induction. Okay, so basically, if you have a conductor, so this piece over here, if you move it back and forth, then inside the conductor, you will have current loops, right? Due to the effect that this is in the electric field. So if you draw a circle there, it's going to be having changing magnetic flux through that circle. So then there will be induced current inside the bar magnetic, okay? So, and then according to the Lenz's law, this should be opposed to the change of it. So if you pull the bar magnetic away of the bar conductor, the conductor piece away from the region of the magnetic field, then the eddy current produced inside would have a direction in this case so that the magnetic force is opposing to the motion. Okay. Now there's several applications of this for eddy current. Okay. So one would be the electric brake. So for the brakes, okay. So when you apply electric brakes, then actually you are applying the magnetic fields around this metal drum. So you can you can have like coils, and then you can send the current through the coil, so then it will produce magnetic field. Okay, so pretty much that's the way the magnetic field is produced in this case. Then because this drum is moving inside the magnetic field, so then there will be eddy currents being induced on this one, and it will have effect of opposing to the motion. Okay, so then you drag down the moving drum wheels in that case. Okay, so that's the electric brakes. Also, if you have a piece of metal, a square in this case, inside the magnetic field. So if you pull it to one end, it's going to be going back and forth without a magnetic field, right? But if you have a magnetic field over here, there will be eddy current induced in the plate here. Will slow down this oscillation quickly. Okay. However, if you do not have a like a intact piece of metal here, if you cut like small pieces openings there, then you will not be able to form a closed loop for the eddy current, like a larger loop there. Instead, you will have small eddy current loops inside these small pieces, and they will cancel out. The effect will be canceled out. Okay, so this is what happens if you have cut the big piece of metals into small pieces, then you'll develop again eddy currents, but in small loops, the neighboring slope loops will cancel out their effect. Okay, so then the damping effect will be not as strong. All right, when you have an intact piece, a big piece inside the magnetic field, so then it will be damped down quickly. You can determine what will be the current, direction of current. So that will be giving you the magnetic force that's opposed to the direction of velocity, okay, in that case. Also, for application here, another application here for garbages, if you want to sort out the metals, you can put a magnetic field here. So as the garbage go down here, because of the eddy current will be produced inside the metal, so then the metals will be tracked over here, okay? Also, for the lab balances you guys use in the lab, if you look carefully, there's magnets here will damp down this oscillation. Otherwise, the oscillation is going to be taking very long time. Okay, so that's the metal piece over there. There's a magnet there, so that damps down. And then another application will be the metal detectors. So you'll have magnet over here, and you're sweeping it across the surface over here. If there's metal piece down there, there'll be eddy current induced, and it will drag this. Okay, you'll feel a dragging force on that and be detected. All right. Any questions you guys have on this eddy current? The section of eddy current? If not, we'll stop here for today for the lecture. And this again, the homework 8 is due tonight. Okay, so make sure you have time to work on the problems. Okay, so I'll see some of you guys for the lab this afternoon, and then the rest of you together in class tomorrow. Okay, see you guys.
Have a great day. Bye.
Thank
Thank
you
you.
too.